Okay, fine. Let's start the second lecture then here. If there are any questions, please put them on the chat window, which I can just see down here. And if there was anything you want to ask about last time, then please do so. What we're going to do today is continue, well, our discussions about the empty set, but also about some other sets, and try and see why we have to think about proper classes, collections of sets which can't be sets themselves. So we'll try and clarify that concept a little bit, and again talk about some other axioms as well, the axiom of subsets, for example. So let's see, where were we yesterday? We had the empty set here. That just said there is an empty set. That is one with no members. And we gave it this name. I can think of it as the class of all of those x's that don't equal themselves. So of course, everything equals itself, so nothing fulfills this condition. So this is an empty class right here. And the axiom asserts that this is then a set in our universe of mathematical objects. This is the Norwegian letter You often see it in textbooks with a 0 with a line through it, and many people think it's a 0 with a line through it. But I believe the story goes that the mathematician André Weil was writing a text and he wanted a symbol for the empty set. And I think his like 10 or 12-year-old daughter, Anna, then said, use Norwegian right? So this is how it's come about, that we have this letter here to represent the empty set. So what we're going to do then is just think about, I'm looking here at examples 1.3, this is line 71 on page 5. Just think about just the properties of this empty set. This is just to fix some notation. So the empty set is a subset of any set or class A here. Right? Why? What does this mean? It says anything that's in here is in here. And that's simply true, vacuously. It says for all x, if x is in the empty set, then x is in A. And that's simply true, because for any x, what I've got here is false, right? So this logical implication is always true, because this is always false. So the empty set is a subset of every set. So in particular, the empty set is a subset of itself. On the other hand, it's not a member of itself, obviously. Because this is supposed to have no members. But there's nothing wrong with this. This set has got one member, which just happens to be this. So that's just using the set inclusion notation. So don't get confused by these things. What is the power set of the empty set? It's the collection of all power set of, in general, of any A It's the collection of x's such that x is a subset of A. By the axiom of power sets, this is a set. Well, we've just said the empty set is a subset of anything. So any power set is going to have the empty set as a member. So a power set of any set, there's always going to be two things in there, the empty set and the whole set itself, because A is a subset of A. So this is at least going to contain the empty set, because the empty set is a subset of this. But there's nothing else. So the power set of the empty set is just the empty set. On the other hand, this is a different matter. Right? This is a set with a bona fide element. Right? I mean, you might want to think about just in general. Power set of any, we call this a singleton set because it's just got a single element. Power set of any singleton. Right? Well, I know that the empty set is going to be in there. Right? And what else can be in there? Well, just the whole set. There. So again, thinking of A as not confusing ourselves, just thinking of A as the empty set over here. We have this here. So internalize these definitions. Make sure you understand the empty set and the fact that the power set of these simple sets gives us these things here. What the universe of sets will look like is the diagram at the bottom of the page. Eventually, the universe of sets so you can look ahead to chapters 5 and 6 for this. I'm going to think of it as it's drawn often as a cone like this. This will be the class of sets such that x equals x. So it will include every set. And we'll start out with the empty set. So we'll build this universe up out of nothing. So V0 is down here, the empty set. And each level will be the power set of the previous level. So V1 will be the power set of V0. We just worked out what the power set of the empty set was. And in general, Vn plus 1 will be the power set of Vn. So we'll build up these levels like this. So Vn plus 1 will just be the power set of the previous piece. And the question then is, like one of these processes I was talking about last time that Cantor came across, we want this to go on beyond stages indexed by the natural numbers. So what we'll see later on, and it's quite natural to do, is because one can show, it's an exercise to show that Vn plus 1 always contains Vn, what we've got is a collection of sets that's being built up like this. after we've gone through the n's, the natural numbers, it's quite natural to take a union of all the sets we've got and then continue the process. But we want to give some mathematical foundation to that. I mean, that's just the kind of the intuitive or heuristic idea. So this is what will come later, is the idea is that we can iterate this power set operation, keep taking power sets all the time, and then at certain limit points, limiting processes will take a union of everything we've got. We'll have to justify we can do that. So this is just lifting the curtain a little bit on what's going to come later. So there's a question here from Xander. If possible, could we clarify the last statement on line 71, example 1.3? Isn't it? Is it meant to be a curly bracket after the S? Okay. I think, well, let me go through it. I think what the question is, here we have on example 1.3. Yeah. The questioner is asking about the last statement here. We have that this set is a member of this one, right? Because this set is here, it's literally a member of this one. So this is okay. On the other hand, this is false. So this is false here. Because this would mean every element of this is an element of this. Okay, here's an element of this one, right? But it's not an element of that one. So this is false here. Okay, thank you. Yeah, do keep the questions coming. I just have to make sure the chat window is a little small and in the distance there. I have to make sure I keep looking at it. Okay, let's go on to 1.2, classes. Okay, so at this point in a live audience, I ask people, hands up, who's heard of the barber paradox? And usually about 25% of the people have. So let's have a poll. I'm hoping you can see that poll there. This is just for fun. Let's see how many people see that and answer it. Oh, you're not supposed to answer the second question yet. You're supposed to just answer the first question. So the story goes as follows. Right? There is an island, and I don't know why it's usually a Greek island, but anyway, there's a Greek, perhaps to do with Greek philosophers. There's an island, and on the island, there's a population of people, and there's a small population. There's one barber who's a man, who's a male. And the setup is that this barber shaves everybody on the island who does not shave them, every man on the island who does not shave himself. So it's a if and only if, right? So if there's a man on the island who does not shave himself, then the barber shaves him. Right? And that's all the barber does, is shave the men who do not shave themselves. The barber is male, it's a very binary society. Right? So then the question is, does the barber shave himself or not? And it appears paradoxical because he's only supposed to shave men who do not shave themselves. So therefore he can't shave himself. But if he doesn't shave himself, then he has to, because he shaves all and only those men who do not shave themselves. So, what's the resolution to the paradox? Is then what I ask next. Does he or does he not shave himself? So now you can answer question 2 that's down on the poll there. Okay, so I guess the barber paradox is getting more famous these days. It looks like 37% of people had heard of this anyway. So, and 45% say he does shave himself, and 55% say the opposite. So if you've heard of the paradox before and you understood it, then you shouldn't really answer the second question. So I think some people have heard the paradox before did answer. Anyway, so the answer is that, I mean, in some sense there's no, because there was no such thing as a paradox. Paradox is always just something that's still requiring an explanation. Right? So there ought to be no unsolved paradoxes. So the solution then in this case is that simply I was just fooling you. Right? All I've done is just describe a situation which can't exist. Because I set it up as a story, you start feeling that, oh, there's some logical question about this. But there's no such island, right? There's no such barber. Right? The whole thing is just because I describe something doesn't bring it into existence. Right? So it was a nonsense in the beginning. So there is actually no paradox there. So the logician and philosopher Bertrand Russell, he came up with a version of this paradox, but it's in logical terms. And the reason he was doing this was he was very much interested in the work of the German logician Gottlob Frege. And Frege was, well, his life work really was his magnum opus was already in the press, and it was going to be published in 2 volumes. The first volume was out. Second volume was due to go to press. And what Frege was trying to do was trying to reduce arithmetic to logic. So he wanted to prove that everything in arithmetic essentially was pure logic. Right? Logical concepts could explain everything in arithmetic. And the idea then would be that we can reduce analysis to arithmetic, and geometry we can reduce to analysis. So this would mean that somehow by progression, all of our mathematical concepts will be seen as just being purely logical concepts. So the logical system that he'd set up, it turned out was flawed. And Russell pointed out this paradox, very similar to the barber paradox, which completely pulled the rug from underneath Frege's system, unfortunately. So Frege's second volume went to press, and he had to put a sort of erratum note in the volume that he'd had this kind of devastating letter from Russell, indicating that there was a mistake in the setup. So let's look at the Russell paradox. And again, could have set a poll up. Some of you may have heard of this. So what Russell did, get another pen. He defined the class of the collection of all sets that are not members of themselves. So it's sort of self-referential, right? You define something, class of X is not a member of X. You know, it's a bit like barbers, men who don't shave themselves. Something refers to itself somehow in the definition here. And as numbered in the text, theorem 1.4 says that this Russell R for Russell, this Russell class here cannot be a set. And this was Frege's mistake. Right? I'm putting it in more modern terms. He assumed that everything you could define like this would be a set. And Russell said, oh, no, you can't. Right? This is wrong. So R is not a set. Okay, so let's see why. And the contradiction you get is just like in the barber. If he shaves himself, he's not supposed to. But if he doesn't, then he must, because that's the definition of this barber. So suppose R is a set. Suppose it's the set Z. Right? You then ask the question, is Z a member of R? Now, most sets are not members of themselves. Right? The set of cows in the field is not a cow in the field, it's an abstract object. So most sets are not members of themselves. So one thinks that this is a pretty large class, if you like. Right? It's only very special sets, if there are any at all, that will be members of themselves, if there are such. So then the question then becomes, is Z a member of R? So altogether, we're setting up a proof by contradiction. We're going to assume that R is a set, and then we'll show that this just leads to absurdity. So this supposition is false, and R cannot be a set, which proves the theorem. Okay, so there's only two cases. We work in classical logic here, binary logic, yes or no. So case one, if Z is a member of R, by being in R, I rubbed it out, what is R? It's a collection of things that are not members of themselves. So if it's in R, it's not a member of itself. But Z equals R. So Z is not a member of R. So from this hypothesis here that Z is in R, we've deduced a contradiction. So this must fail. So it must be that Z is not a member of R. And you can see it coming now, right? We get a contradiction from this as well. But if Z is not a member of R, and we know Z equals R, I've got Z is not a member of Z. But that's just the condition to put Z into R. And thus Z is in R. So it's a contradiction. Okay, bolt of lightning. Down here. So then our supposition overall was that R could be a set was wrong. Right? So R is not a set. There's no set Z equal to R, right? Which is what we were trying to show. Okay. Does anybody want to say anything about that? So it's a knockdown argument. Right? And as I said, it devastated Frege's system, and he spent the next few years trying to fix it. But in the end, it was kind of fundamental to the way that his system was set up, that this became a flaw. Yes, Russell has doomed him there. Right. Okay. So the realization was then that we've really got two kinds of objects floating around here. If we have sets, we're going to have classes. And we're going to have these things like there's R right here, which can't be sets. So these classes here, we'll call them proper classes because they're not sets here. So the moral of the story is we have to deal with proper classes. So we have to accept that there are classes which are not sets. So we call these proper classes. Here. And we'll see some examples later. Proper classes, on the whole, you want to think of them as being like they're kind of too big. They've got too many things in to kind of be sets. I mean, that's one way of, as a first approximation of thinking about them. Most sets are not members of themselves. Here. And what the early people thinking about set theory, how they thought, well, there's a sort of, well, not a workaround, but they realized that they were going to have proper classes, but they also wanted to kind of axiomatize sets. And so what Zermelo did was he thought, okay, what we'll do is this kind of definition is perhaps pulling in too many things. Perhaps this is at the root of this problem. What we'll do is we'll restrict the kind of definitions we put in here. So this gave rise to the next axiom at the bottom of page 6, the axioms of subsets. Here. So phi is a formula here, or an expression, and it gives us some well-defined property of sets X here. And going over to the next page, 7. Then for any y, so again, lowercase here, so I'm thinking set y here. This class, the collection of x's in y, such that phi of x holds, then this is a set. So again, what the axiom does is declare that a certain class can be considered a set. And there's sort of two things to note here. Right? So the difference with the Russell class here is I'm restricting the scope of the things I'm talking about here. I'm only looking at x's that are in y, in this set y. So I restrict attention to a set. Then anything I can define, if I keep my attention restricted, this is safely also a set. The second thing that you should pick up on is the fact that this is a little bit vague down here. Right? I've just said let phi, well, I haven't written it, but let phi be an expression which gives a well-defined property of sets. I mean, so you should be asking, what does this mean as well-defined? That's down here. He hasn't really defined that. And it's true, I haven't. Right? So I'm leaving that a little bit vague. If this was a course in more formal axiomatic set theory, like the 4th year course, I'd be saying, this formula phi has to be written in a particular logical language. Right? And I'd specify what the language is to make a completely clear watertight definition here. But I'm leaving that a little bit vague here. So I haven't said exactly what I mean by a well-defined property here. Yes, so as Levent asked, can I define what I mean by well-defined? Well, no, I can't, and I'm not going to in the moment, right? In another course, I talk about formal languages, and there'll be an expression in that formal language. So let's do corollary 1.5 here. Let V denote the class of all sets. Then V is a proper class. So proof here. Again, by contradiction, suppose V is a set. Suppose it was a set Z. Now I could then write that R, right, this is the collection of x's in Z, such that x is not a member of X. Now I just claim this is a well-defined property. This makes sense. Everybody knows what this means. It's not a member of itself. So here is a well-defined property phi, right? And I'm restricting it to the elements of this set Z here. By the axiom of subsets, this is a set. But we've just proven in the previous theorem that R is not a set. Okay, so this will be a contradiction. So our supposition that V is a set is false. So by the axiom of subsets, R would be a set. Okay, that will be a contradiction. So V is not a set. So V is a proper class. Okay, again, it's a big object. It contains everything. Okay, moving on to the next definition, 1.6. Our big union Z here. So this makes sense whether this is a lowercase or an uppercase Z, right? So whether this is just a set or a class. Right? It's the collection of elements of Z here. So it's the collection of x's so that there is some t such that x is in t and t is in Z. So when I say union, this big U stands for union, it's the union of all sets T that are in Z. That's what this would mean here. I look at any T that's in Z. I look at anything that's in one of those T's, and that's in here. So this is the union of all of the T's that are in Z here. So examples. Suppose I take the set which has just this unordered pair of A and B in it. So this is my Z here. And this should be the collection of x's so that there is something in here such that x is in it. Well, there's only two things in here, A and B. So this is essentially the set of x's as x is either in this A or x is in this B. So actually this is just the same as A union B in our ordinary mathematical sense here. What is the union of singleton set? Well, now there's only one choice of T here, if this is Z. It's just this A. So the definition here is just saying this is the collection of x's such that x is in A. So this is just A itself. What we've got here is something that's really quite flexible because there are no restrictions on this Z here. It doesn't have to consist of just two things, so we have an ordinary A union B. If I've got sets A1 up to AN here, then the union here, this is A1 union A2 up to AN. But we can also take here perhaps an infinite collection of things here. suppose Z is this. Right, an infinite collection, which I've enumerated and I've shown them, A0, A1, A2, AN. So the notation is supposed to indicate I've got a little a for index by each natural number. And then here in this case is, well, the union of these z's here is, I want to write this like infinitely long formula here, but I don't really like my formulae to be infinitely long, so actually I'm just going to write it like this. It's the union of the n's in the natural numbers of these ANs. Or another way I could just write this is, it's the union of here, union of the ANs for n in n. So do practice these big union symbol. Get some facility with this. It's going to appear a lot, right, in what comes here. So these are two different ways. This is a kind of more usual mathematical way of describing what this union is. And I mean, well, set theorists would write this as well, but this is perhaps more set theoretically closer to what our other notations are like. But here we can do things which are much more flexible. We don't have to stick with this, just things indexed by the natural numbers. So we could have unions indexed by other sets. So suppose I is a set. And it's an index set. So for each little I in big I, we have a set AI, like this. Then I'll say big union of here, these AIs, indexed by this here. This is big union of a collection of AIs for I in I. So this is very useful. I mean, there's no restriction on what kind of set this has to be. This doesn't have to be the set of natural numbers. Right? The set of reals might be anything. Right? But the big union symbol says I collect together all of the elements of these different AIs together. So this is the set of Z's. Let's choose a different one, set of X's, so that there is an I in I with X a member of AI. So this is a very useful notation. And we have an axiom that says that we're justified in taking these unions. So this is the axiom of unions. For any set Z, this is a set. And again, somehow the idea is that we're not throwing in too many things. It's not getting too large. And there's a picture that I could have drawn before. Here's Z And Z consists of all of these sets. And these sets contain various gadgets. Then the big union of Z is just a collection of all of the gadgets that are in there. So I can write big union of Z is just this, right? All I do is put all of these things together. That's what the big union of Z would be.